Have you ever wondered how Uber matches you with a driver in seconds? Among millions of moving parts, it is not just a simple search. It is a high-concurrency, low-latency distributed systems challenge. Today, we are going to peel back the curtain on the algorithms and architecture that make it happen. If you are an engineer, you know that scale changes everything. Why can't we just use a standard SQL query? You might think. Select driver from drivers where distance is less than 5 kilometers. But imagine doing that for every request, every second, across a global fleet. A linear scan of millions of rows would crush your database latency. We need a way to narrow the search space before we even start calculating distances. This is where geospatial indexing comes in. Instead of treating the world as a flat list, we divide it into a grid. Think of it like a giant cabinet where every drawer represents a specific geographic area. When a rider requests a trip, we only look in the drawers immediately surrounding them. This reduces our search complexity from linear to logarithmic or even constant time. One common way to do this is with a quad tree. We start with one big square. If it contains too many drivers, we split it into 4 smaller squares. We keep nesting these squares until each leaf node has a manageable number of data points. This hierarchical structure allows us to traverse the tree quickly to find the exact bucket we need. Google's S2 library takes this further by using Hilbert curves. It maps two-dimensional coordinates onto a one-dimensional line while preserving locality. This means that points that are close together on the map stay close together in the index. For a developer, this is huge. It means we can use standard B-trees or sorted key-value stores to perform incredibly fast range scans. But Uber actually created its own system called H3. Why? Because squares have a problem. The distance from the center to the corners is different than the distance to the sides. Hexagons, however, are much more uniform. Every neighbor of a hexagon is the same distance away. This makes calculating coverage and movement much more accurate for dispatching. Now let's look at the request flow. When you hit request, the ride request goes to a dispatcher service. This service queries the H3 index to find available drivers in your cell and adjacent cells. But here is the catch. We don't just want any driver. We want the one with the lowest estimated time of arrival, or ETA. State management is critical. Drivers are constantly moving, so their H3 cell ID changes every few seconds. Uber uses a high-performance in-memory state store to track these updates. If this service lags, we might send a request to a driver who has already moved 2 miles away. We need sub-millisecond updates to keep the system fresh. To handle global scale, Uber shards the data geographically. A request in London doesn't need to know about drivers in New York. By sharding the state based on city or region, we can scale horizontally. However, we must handle boundary conditions where a rider is on the edge of 2 shards. This is where a consistent hashing layer comes in handy. The dispatch loop uses a technology called ringpop, a gossip protocol-based membership system. It allows the dispatcher to know which servers are healthy and which ones are responsible for which geographic area. This ensures that even if a server dies, the matching process for a neighborhood can be quickly reassigned without a central bottleneck. Remember, the nearest driver isn't always the one with the shortest distance. A driver might be just across the river, but the nearest bridge is 5 miles away. This is why the system must integrate with a routing engine to calculate the real ETA based on road networks and traffic, not just as the crow flies distance. Instead of matching the first driver found, which is a greedy approach, Uber often uses batch matching. We wait a few seconds, gather all requests and all available drivers in an area, and then solve a global optimization problem. This maximizes the overall efficiency of the network, reducing wait times for everyone, not just the first person who clicked. What happens when 2 people request the same driver at the same time? We use distributed locking or atomic, compare and swap operations in the state store. This ensures a driver is never double booked. If a driver rejects a request, the system immediately puts them back into the pool and moves to the next best match in the queue. Putting it all together, we have a massive distributed system. From the mobile apps to the gateway, the dispatching engine, the H3 index, and the routing services, all communicating via high-speed RPC calls. This architecture is designed for 5 nines availability, because if the dispatch system goes down, the entire business stops. So the next time you open the app and see those little cars moving on the map, remember, you are looking at a masterclass in geospatial indexing and distributed systems. It is not magic. It is just very, very good engineering. Keep building, keep scaling, and I will see you in the next deep dive.